Question 2. Oxides have different types of bonding. Water has hydrogen bonding. Complete the diagram below to show hydrogen bonding between two water molecules and between the H1 molecule shown and one other water molecule. We'll read the question properly. Include relevant dipoles and lone pairs and label the hydrogen bond. So let's ignore this bottom bit for now. Focus on the diagram. Hydrogen bonding diagrams, they're going to come up again and again because hydrogen bonding can be applied to a whole variety of other chemicals, organic and inorganic. So for example, we can use hydrogen bonding to explain the solubility of alcohols and the solubility of carboxylic acids as well. So it's important that you learn the basic principles behind how to draw a hydrogen bonding diagram and what the examiner will be looking for in terms of the detail that you put on those diagrams. It's kind of alluding you to the fact here, these two statements are important things to factor in. So let's start off first of all by putting the relevant dipoles and lone pairs on the water molecule that's been provided for us. Oxygen is more electronegative than hydrogen, so our dipole will have a delta minus and delta plus in that formation. So delta minus on the oxygen and delta plus is on the two hydrogens. Lone pairs, well, there's obviously no lone pairs on the hydrogens. Their only electron is caught up in the covalent bonds here. Oxygen's got 6 on its outer shell, therefore there's 2 pairs of electrons left over. There's 2 lone pairs. Let's clearly show them 1, 2, 3, and 4. Okay, 2 lone pairs on an oxygen. So let's draw a second water molecule. Let's draw it in the same manner as what's been drawn there. Put the lone pairs on. Delta plus, and delta minus on that oxygen there. So there's our relevant dipoles on lone pairs. And so the hydrogen bond, if we think about the definition of a hydrogen bond, it's the intermolecular force between the lone pair on a highly electronegative element of one molecule and the hydrogen atom of another. So in this instance, you can draw the hydrogen bond between the oxygen of this one here and the hydrogen of the one you've drawn, or between the hydrogen of the one that's there and the oxygen of the one you've drawn. It doesn't matter which one you do, and you haven't got to do more than one. So bearing in mind of the way I've drawn these two molecules, I'm going to show my hydrogen bond here between the oxygen of the water molecule that's provided for us and the hydrogen of the one I've drawn. So your hydrogen bond should always be drawn as a dotted or dashed line between the two molecules. Okay, never draw a solid line because these are indications of full chemical bonds, covalent bonds in this instance. So don't draw a solid line between the two. It must be a dotted or dashed line. It doesn't matter which one you choose as long as it's not solid. And the bond must go, the hydrogen bond must go from the lone pair on that oxygen. It's one of those key details that students commonly forget. It's only worth 2 marks, this question. And if you miss that, you lose a mark instantly. 1 mark will be for the dipoles and labelling the hydrogen bond. The second mark will be indicating that that's coming from the lone pair. So make it nice and clear the hydrogen bond is attached to the lone pair. And it says there to label it. Believe it or not, if you don't do that, you drop a mark. It's a very silly thing to lose a mark for. So label the hydrogen bond nice and clearly, even though it's obvious that is what it is, but the examiner's asked you specifically to label it, so make sure you do that. In part 2 of this question, state and explain 2 anomalous properties of ice caused by hydrogen bonding. So for this one, there's 3 anomalous properties you might have looked at before. So you would have looked at the fact that ice is less dense than water, which is unusual because you'd expect the solid to be more dense than the liquid. The fact that water's boiling points are, well, the boiling point of water is 100 and melts at 0 degrees C, which actually is unusually high for the type of molecule that water is. So there's evidence that hydrogen bonding is increasing the boiling and melting points more than they should normally be. The third one, which is one to avoid, but you could mention it if you're stuck, is the high surface tension of water. So water is it's got unusually high surface tension. That explains a lot of the physical properties of water as well. So whenever you get these 2 anomalous properties answers questions, I would always go for the density explanation and the melting and boiling points. But you've got to watch the wording to make sure you've expressed yourself in the right possible way. So first of all, now if we go for ice is less dense than water. Okay, that is your first anomalous property. So you've stated it, you've now got to explain why that is. Okay, this is because the hydrogen bonds become rigid. And when they become rigid, they push the water molecules away from each other. So we increase the space in between the water molecules. And what it creates is a structure known as an open lattice structure. Okay, so there's more space in between the water molecules than in ice than there is in liquid water, and that's why it's less dense. The second one, this one we can talk about the unusually high melting and boiling point. Okay, and it's that first word I've written there which is the crucial one to include. If you just say high melting and boiling point, then you're actually stating something that's incorrect. It's not a high melting and boiling point, it's an unusually high melting and boiling point, because in the grand scheme of things, boiling 100 degrees isn't that high. You think about some of your giant covalents and giant ionic substances and your metallic substances, their melting points are in the multiple hundreds. So actually, it's not high, it's unusually high. The hydrogen bonding present is making that melting and boiling point higher than it should be. So without the hydrogen bonds present, water's boiling point would be somewhere in the negative numbers. Okay, so it's an unusually high melting and boiling point. And this is all to do with strong hydrogen bonds. Needing more energy to overcome than permanent dipole-dipole interactions. Which is what could also form between polar molecules.